Grams cancel out, degrees Celsius cancel out.
And it's probably calories.
Where did you get the 40 from?
Because the problem is like, we're taking the water from 20 degrees Celsius to 60 degrees Celsius.
So you subtract?
Yes.
Okay.
Change in temperature, this is delta T, change is always final minus initial. 60 minus 40. Or, second answer is, because Latoya said so. Nah, probably better, it's what Latoya told me. All right, questions to hear? Let's make it more complicated.
Mister, so whenever you do this equation, you're always supposed to put 1 Kelvin, over grams degrees Celsius?
1 calorie per gram degree Celsius. That is, if I want the specific heat of water in calories, yes, I would use that number. Of
And
liquid
this-
water.
And then the specific heat in joules, you write it just like that?
Yep. These are constants. This is the type of thing that if we're dealing with water, you would look on the top of the first page, and that's where I'd give you that kind of information. Or if I forget to write that down, then I'll have it either in the problem or someone asks and I write it on the board.
Oh,
But I'm not expecting you to memorize these two things.
okay.
Although you should be able to recognize it's 1 in some unit system,
Yeah.
but then again, answer to everything is 1 if you pick the right units. Actually, before I draw that picture, so instead of doing 20 to 60 degrees Celsius, suppose it starts out at 30 degrees Celsius and I want to take it to 70 degrees Celsius. How much energy is required now?
So is it always good to
Is it
first,
still 50 milliliters?
Yep.
is it always good to find the change in temperature so we can know how much energy was used?
It'll be crucial to find the change in temperature, to know how much energy was used.
Isn't that still 40?
It'll be 40 degrees Celsius. Is
Yep.
it?
The change in temperature is the same.
Same.
And therefore, I heard somebody say it, I was over here when I heard it, so I assume somebody over here said it. But it'd also take 2,000 calories. Or, flashing back to something we did 2 days ago, 2 calories with Dixie. The food calories.
2 calories. We didn't do that.
I talked about the relationship between calories and food calories.
Oh.
Now, food calorie has a capital C, the physics chemistry calorie has a lowercase c.
Yeah. So it'd only be 2, if we was talking about food, it'd only be just 2
Right.
calories.
So if you have an ice cube in your mouth and you are melting it, the energy is being put into the ice cube.
Yeah, from me.
And that energy's gotta be coming from somewhere.
Me. Uh-huh.
And so that there was, at some point, the little factoid of how many food calories, well, they just called it calories, how many calories you would lose melting ice in your mouth. Because that energy is coming from you. And as energy is coming from you, you were losing energy, therefore you were losing mass.
Alright, so I'm a little confused now. So, 2 food calories equals to 2,000 physics calories?
Yes.
Cause you said before it was like.
All right. How about that? We'll make it simpler. Let's ignore the whole food thing.
That was better.
All right. Now what I'm going to do is we're going to, so still 1 calorie per gram degree Celsius. And we're going to take it from 275 Kelvin to 315 Kelvin. pull out our equation over there. I know that Q is equal to MC delta T. My mass is 50 grams. C is 1 calorie per gram degree Celsius. And the change in temperature is 40 Kelvin. How much energy now?
Is it still the same?
It's still 2,000.
Sorry,
Is it still gonna be, the 2,000, right? 2,000 calories?
how do we resolve this whole, I got degree Celsius here and I got Kelvin there.
Can you convert anything? I mean, they're both temperatures, right?
Both what?
Temperatures?
Yeah, they are.
So do you convert anything?
We can.
Okay, what do you do?
How do you go from degree Celsius to Kelvin, or Kelvin to degree Celsius?
It's a certain number, but I don't know the number.
So is
Okay.
we doing degrees Celsius plus the 273.15 to get Kelvin?
All right, so that's the number right there that Ethan was talking about. All right, so 0 degrees Celsius is 273.15 Kelvin. So from degrees Celsius, I had 273.15. If I had started Kelvin, I would subtract 273.15. Or let's just simplify it to 273. Doesn't change what I'm trying to get across here.
So we're subtracting that from 2,000?
Now, this is temperature here. So if we subtract 273 from this, so this is 2 degrees Celsius. And from that, so what's my change in temperature in degrees Celsius? I think somebody said it. Yes.
So each time we wanna convert any temperature, or is that just converting Kelvin?
That's Kelvin to degrees Celsius.
Okay, so we use that number, 273?
Right.
Okay.
Or if you want to be specific, add 0.15. But now notice, when you're dealing with change in temperature, Kelvin and degrees Celsius gave you the exact same change. So this only works if you're dealing with a change. So the answer is, as Ms. Goff originally said, it's still 2,000 calories, because 40 Kelvin in change in temperature is the same as 40 degrees Celsius in change in temperature. Kimberly?
Is that minus 42 degrees Celsius? So the change is 2 degrees Celsius?
Oh, that goes from
Oh.
initial final. Sorry, not a subtraction. Was it in dash? Questions here?
I feel like I had a brain fart.
Sure.
So you subtracted, when you got 40, you subtracted the 2 from the 42.
Yes. Yeah, same thing as you did before when you subtracted the 20 from the 60.
Mhm.
All right. Make it more complicated.
But that was complicated?
Aluminum block. Let's give it. $50-gram block at 70 degrees Celsius. And the way you would do something like that is, this is an experiment we're not doing, but in a longer course we would. You basically get water up to whatever temperature you want it to be. You put the cube in there and let it sit in there, and it'll start absorbing the heat that's in the water. And so that's how you, and if it's in that 70-degree water for a couple of minutes, it would be close enough to 70 degrees. And so we have water here at, we'll say roughly room temperature, 20 degrees Celsius. And let's give this, let's keep it the same mass. 50 grams of water. Keep those in. So they're starting, these are the initial temperature, 70 degrees Celsius, 20 degrees Celsius. We will make the nice little assumption that energy is only exchanged between the aluminum and the water. There is no energy at all that goes out into the environment. So what's going to happen is, which one is going to lose energy, which one's going to gain energy when I put them together?
Block loses, water gains.
Say it again?
The block loses energy and the water gains energy.
Yes. So the final temperature has got to be somewhere between 20 and 70 degrees Celsius. So block will lose, water will gain. Well, how much will the water gain? Well, it's going to gain energy, and the block is going to lose energy. We'll do it this way. Q for the aluminum plus Q for the water is equal to 0. All that says right there is that when I take the amount of energy from one, I'm going to give it to the other. Matter of fact, I can take that over to the other side. I could also write it this way I was about to write it before. Q aluminum. So the energy that is gained by the aluminum, or that is lost by the aluminum, is the negative of the energy of the water. So if this is negative, Q has to be a positive number. If this is positive, Q has to be a negative number. The formula, we have only one formula there. This is M of aluminum, C of aluminum, delta T aluminum, going to be equal to negative mass of water, specific heat of water, change in temperature of water. One gains, the other one loses. Again, this is just a more symbolic way of saying the exact same thing. Now we plug and chug what we can. I got mass here, mass of the aluminum. I gave that to you, that's 50 grams. Specific heat of aluminum. And I chose aluminum because I'm pretty sure I wrote it down. There we go. 0.215 calories per gram degree Celsius. 0.215 calories per gram degree Celsius. Times the change in temperature. I don't know what the final temperature is. That's my unknown. Minus my initial, which is 70. And that's got to be equal to, well, just plug in. I got negative, mass of my water is 50 grams. Specific heat, 1 calorie per gram degree Celsius. And change in temperature is, I don't know what the final temperature is, but it's, so that's my unknown. Now, I will tell you that the problem that we're doing right now, I consider to be the hardest of the specific heat, the hardest of the thermodynamics problems for Physics 110. So try not to psych yourself out, just so if you can handle this, you can handle any of the rest of the stuff. If you can't handle this, you can handle the rest of the stuff. All right. The math problem, let's just, I know what my final answer is going to be, the units of the final answer. What will the units be for my final answer?
Calories.
What am I trying to find?
Oh, wait, it might be joules.
What am I trying to find?
Trying to find change in temperature.
So when is the
Celsius.
Celsius?
Degrees.
There we go. I heard degrees something.
Degrees Celsius.
Degrees Celsius. All right. My final answer is going to be in degrees Celsius.
Okay.
So I'm just going to simplify I'm just going to rewrite this except make it look more like a math equation. So I'm just going to not write my units. So I have 50 times 0.215 times t minus 70 equals negative 50 times 1 times t minus 20. It might still be daunting for some of you, but at least it's not as cluttered as what we had. So let's solve. Now, for those a little bit more math sophisticated, you can recognize that I'm multiplying both sides by 50, so I can just get rid of 50 if you want, or you can keep it in, doesn't matter. Let's just keep it in for right now. So 50 times 0.215,
10.75.
10.75 times t minus 70 equals, and then I got this one, negative 50 times t minus 20. So now I got a number outside a binomial. Distribute. Multiply this times that, then this times that. I got the first one. That's 10.75t minus
70.
yeah, 10.75 times 70. 752.5 equals, over here, minus 50t, just multiply times the first thing, then multiply times the second thing, plus 1,000.
For your final answer, did you get 2.8? No, I'm sorry, 28.84,
28.84
something like
is
that.
for the final answer, we'll find out.
Okay.
I make up the numbers at the moment, so I don't know what the answer is gonna be yet. That seems reasonable, but let's find out.
Okay.
All right, so now I need to get the t's on one side, the non-t's on the other, so I'm gonna bring this over to the left-hand side, bring this over to the right-hand side. So I add 50 to both sides, add 50t, so I get 60.75t. And over here, I'm adding that to the other side, so that's 1752.5. And for those who missed that,
I did.
I'm gonna add 50t to both sides. So that it disappears from this side and shows up on the other side. And then the 752.5, I want to get over to the right, so I'm going to add it to both sides. So on the left-hand side, these cancel out, and I'm left with 10.75 plus 50t, or 60.75t. And on the right-hand side, I got 1,000 plus that, and it gives me this. I assume you've done this, that's what you did.
Mm-hmm.
And then we need to get t by itself, so let's get rid of that 60.75. And you got 28.8.
847. Or can we do 8.5?
Sure.
Not 8.5, I'm sorry, 8.5.
Yeah, sorry. Apparently I went with the spirit of what you were saying. And then let's finish it off. There we go. Now, questions up to here before we talk about whether this answer makes any sense whatsoever.
I have a question. So you're just ignoring the negative in the t's?
I
To
think
get the
that
plus.
negative right there,
No, in the parentheses. or do those cancel out? Cause I thought that'd be a negative 20.
Negative times negative is probably.
Yes.
What about on the other side?
Over here, I got positive 10.75 times, a positive number is positive, positive times negative is negative.
Okay.
And then over here, negative times positive, negative, negative times negative, positive.
Okay. I was a little confused.
All right, so let's talk about if this answer makes any sense whatsoever. Let's look at our specific heats. Specific heat of water, 1 calorie per gram degree Celsius. Here, I got 0.215 calories per gram degree Celsius. So aluminum, water. Which one is easier to change the temperature of?
Aluminum.
Yeah, the smaller this number is, the easier it is to change. You can almost think of specific heat as thermal inertia. The smaller the number, the easier it is to change. So when I put them together, the aluminum is going to change its temperature more than the water will. Therefore, I would expect the final answer to be closer to the original temperature of water than for the aluminum. I expect it to be between 20 and 70 degrees, and I expect the final answer to be closer to water, and that's satisfied there. So this makes sense. Yes, Lacey?
How did you get the 0.215?
I gave it to you.
Oh.
That's a constant. People have measured it and made it available for us to cherish.
Alright.
Yeah, that, I'm not expecting you to know the 0.215 calories per gram degree Celsius. I would give that to you. All right. Let's double check our work, not by going through all that again. How much energy did the aluminum cube lose? Well, that's the formula I'm plugging into.